Hi, everyone. I know most of you don't know me. My name is Pamela Mukumba, and I went to the University of Zambia a very long time ago. Now, yeah, so my talk is on copper grade distribution across the Com and Chambishi at Mingomba, a single fluid redox model. So I've made this as simple and as easy as possible because this is for my students, really. Yeah. And so I work at Cobalt Metals, but I mainly work at Mingomba on the main Mingomba license and outboard drilling that Wilson and Alpha presented on. So sorry, I don't have screen here, so I'll have to look at that. Yeah. Okay. So lucky for me, a lot of people have presented on this, so I guess now we can locate ourselves. We know where Mingomba is. So we are actually a few kilometers from Chilabombwe town, near the border. That's where Mingomba is. We have Kogunkola to the south and Lubambe to the northwest of us. So stratigraphy, this has also been touched on briefly, but we have our oldest rocks at Mingomba, Katanga basement, and then we have early rift sediments in the Mindola clastics, and then the Kitwe, and the Kitwe is what hosts our mineralization. So we actually see mineralization in three horizons. We see mineralization firstly in the COM, the Copper Belt ore body member. So for the rest of the talk, I'll just be referring to it as the COM. And then we see a bit of mineralization in the Nchanga, and we see mineralization as well in the Chambishi. But for this talk, I will only concentrate on the COM and the Chambishi because that's where the mineralization is laterally extensive. So I think Wilson and Alpha did give the geology of the strat from the Abaron Branch are going up, so I will mostly concentrate on the Chambishi. So we see the Copper Belt ore body member that represents our first major flooding. And then above that, we have the Rokana, and then the Nchanga, and then we have another flooding surface in the Chambishi, and then we have the Konkula conglomerates that cap the Chambishi. So Mingomba is not unique when it comes to stacked ore bodies. So there are several stacked ore bodies on the Zambian and Congolese copper belt, and some of the ones that are on the screen are some of the examples that I'm giving today. So we have Mfulira, we have Kinsenda, and we have Nchanga as well that has stacked ore bodies. So this is just a schematic section of what you'd see at Mingomba. So this is the southwest northeast section. So you have your basement at the bottom, then the Mindola clastics. The red is the copper belt ore body member, COM, then the Rokana Nchanga, then the Chambishi. And so for this talk, I'll be concentrating on the mineralization in the COM and the Chambishi. So what hypothesis were we testing with this single redox model? So to give you a background, because we have to drill through the Chambishi before we get through the COM, a lot of people here, a lot of geologists actually who are here from Mingomba, every time would see bonite or would see a bit of chalcopyrite in the Chambishi, people would be worried, right? And say, oh, then the mineralization in the COM is not going to be as good. By saying that, they're already invoking a single redox model because they're saying it's the same fluid that's mineralizing the COM and migrating up to the Chambishi. So the hypothesis that we're testing here is single fluid, progressive copper reduction. So mineralization timing is synchronous. Both horizons were formed by the same copper-rich fluid. The COM as the first reductant intersects the fluid before the Chambishi member, resulting in higher grades. So here I'm invoking that the reduction potential of the host rock controls where the highest grades form. So our prediction, COM carries systematically higher grades than the Chambishi. Falsification criteria would definitely be if we see that the Chambishi has higher grades. And then another prediction would be chalcocite dominant in the COM and chalcopyrite and pyrite dominant in the Chambishi. This also would be falsified if we saw a lot of chalcocite in the Chambishi. And then another one is looking at vanadium titanium ratios. I'm predicting that they would confirm that the COM was actually deposited under more reduced conditions. And then a falsification criteria here would be if you see higher vanadium titanium ratios in the Chambishi. And then another one is rhenium. I'm going to explain, I have plots that will explain why I'm using these. But rhenium concentrations are elevated in the COM relative to the Chambishi. The falsification criteria is why you see rhenium concentrated in the Chambishi as opposed to the COM. So, fasces, I think Elizabeth has already touched on this. I can't do it better than her. So, but basically, these are some of the fasces that we see. We can see the planar laminated, she said she didn't want to call it a siltstone, but we do call it a siltstone at the top. And usually, this is almost the way we see them. So think of the core at the bottom as the base of the comb, and then as you progress to the top, you see more laminated fasces at the top. And then for Chambishi, you see mostly mineralization is hosted in dolomitic siltstones, but you also see mineralization in a flooding surface at the top. And also we see in the middle, I think Elizabeth did talk about soft sediment deformation. We do see that in the Chambishi. But one of the things I wanted to show you is just the setting for these two horizons. They do not have the same setting. So when you look at the COM, what you have below conglomerates and sandstones, as Elizabeth alluded to earlier. And then you have the COM, and then above that is capped by the Rocana, which are caustic sandstones. And the grade profile, you can see, usually that's a typical grade profile that we see, and we call it bottom loaded because you see at the redox front is where we see the best grades. And then by the time I get into the Rocana, the grade has died out. But when coming down to the footwall, the grade doesn't die out abruptly. So you still see that transitional grade reduction until you get to no grade at all in the Mindola. But when you look at the Chambishi, what you see is, yes, below it has the Nchanga. The Nchanga is usually sandstones, silty sandstones and sandstones. But just below the mineralized portion within the Chambishi, you see a dolostone. And so we think of that as an aquiclude, right? So the COM has aquifers both below and above. The Chambishi similarly, but before we get to the aquifer, there is an aquiclude, there is a carbonate that's below the mineralized portion in the Chambishi. And then above that, we have the Konkola conglomerate. So now, grade distribution. So this is COM grade distribution. So the ones that have been highlighted in red, that's our high grade trend. I think Elizabeth did talk about that as well. And then, so you see that we have a southwest, northeast high grade trend. And then for the Chambishi has been highlighted in blue. So we have a few localized high grade portions where the Chambishi is high in grade, but I've also added the COM outline so that you can see the intersection where you have high grades in both the COM and the Chambishi. One thing that I forgot to mention is for both of these maps, this is just based on the entire COM and the entire Chambishi with no cutoff. So the grades look low because the Chambishi is sometimes 28 meters, but only 5 meters of it is mineralized. So that's why it looks like, oh, but why are we talking about this? It's not worth it. But it's because this has no cutoff to it. But when we do add a cutoff, sometimes we tend to get 4 to 5 meters at even 3% in the Chambishi. Yeah, so it is significant. And so we do see a mineralogy zonation when you're coming from the COM going up to the Chambishi. And I think this is one of the reasons that made us say, okay, maybe it is the same fluid, because we see that the COM is mostly predominantly chalcocite. We tend to get some bonite sometimes, rarely chalcopyrite, unless we're dealing with the western domain, which I'm not going to go into today. But when we get to the Chambishi, what we see is mostly bonite, chalcopyrite. In a few holes, we see chalcocite. I'm going to show those, and then chalcopyrite, and eventually we do see pyrite as well. So it is a classic of vertical zonation from the COM going up to the Chambishi. So we've done a lot of fences across the high-grade zone, along the high-grade zone, and the results are almost always the same. But for this talk, I'm only going to concentrate on two fences. So the first fence is along the high-grade trend. So that's my, from KN 201 all the way to KN 234A. Reason why I've chosen these is when you start from KN 201, that's a high-grade hole when it comes to the COM. But by the time you're getting to KN 234A, the COM is almost barren. So I'd like us to see what's happening along this trend, okay? And so all these are just on a Chambishi grade map without any cutoff. So vertical zonation. So at KN 201, you can see that the COM actually is, it has chalcocite, mostly chalcocite. What you see with the oxides rimming is just an artifact of the fact that with this one, I'm just using copper-sulfur ratios. So what it does is if the copper-sulfur ratio is more than 3.7, the ratio is more than 3.7, right? Then it assumes there's something else that's adding to the copper. So you will see that, you see the oxides rimming. For most of them, you see a bit of oxides only in your acid-soluble assays, but in the COM itself, we don't see oxides as much. So you see at KN 201, we have chalcocite. By the time you're getting to the Chambishi, you have oxides and a bit of chalcopyrite at the top. And then KN 210, a very high-grade hole as well. We see that we have chalcocite and a bit of bonite. By the time you're getting to the Chambishi, it's all oxides. And then at KN 217, what you have is chalcocite and bonite. By the time you're getting to the Chambishi, this one is one that I want you to keep in mind, KN 217. So it's a unique one because we see chalcocite in the Chambishi as well. So we see chalcocite, we see bonite, and a bit of chalcopyrite in the Chambishi. And then by the time you get to KN 234, our COM is almost dead. So it's 0.8%. But then the Chambishi picks up grade. So that's for the entire Chambishi, but it's still at 1.47%. And then, so we wanted to look at redox geochemistry. So just looking at proxies that can tell us more about our rocks, right? So one of the ones that we chose was vanadium over titanium. So this one is just normalized vanadium. And we're normalizing it with titanium because for the COM and the Chambishi, you have siliclastics, fine-grained siliclastics, but with carbonate. And titanium, we know, is not affected mostly by carbonates as opposed to aluminum. So that's why we're using it. But one of the things you see is, because this, on the vertical scale, you see it's the same scale across all the holes, you see that in almost all the holes, the vanadium is high. So this is telling you that at the time of deposition, really, the COM was a reduced rock, right? And then rhenium is being used as a fluid interaction indicator. So at Mingomba, you only see rhenium where you have copper. When there's no copper, you don't see it. So we're using it as a fluid interaction indicator. And you see that from KN 201 all the way to KN 217, the rhenium is higher. But by the time we get to KN 234, that's almost barren. The rhenium is higher in the Chambishi compared to the COM. And then using ferrous and ferric iron, you can see that in almost all the holes except 234, the COM is in a more reduced state compared to the Chambishi. But at KN 234, you see that the iron specification picks up. So KN 234, the Chambishi is more reduced. So this is the second fence that goes across our high-grade trend. So it's coming from northwest, going southeast, from KN 242A to KN 211. So here it's the same concept, where you're starting from a high-grade hole all the way to KN 211. that where the comb is barren. So the same thing, vertical zonation. At KN 242A, we see chalcocite in the comb, and then there's a bit of bonite and mostly chalcopyrite in the Chambishi. At KN 220, we have, KN 220 is a bonite-dominated hole, but it has chalcocite as well. But by the time I get into the Chambishi, you only have a bit of bonite and mostly chalcopyrite. KN 215 and KN 217. So this is another hole that you should keep in mind. So this is another hole where you see good mineralization in the Chambishi, but also good mineralization in the comb. So here you have bonite and chalcocite in the comb, and then you have bonite, chalcopyrite in the Chambishi, and just a little bit of chalcocite. By the time you get to KN 211, it's completely barren. So there's nothing in the comb. But you see what happens to the Chambishi, it picks up grade. There you see chalcocite, and you see bonite. The same thing when it comes to vanadium and titanium. You see that vanadium is almost constantly high in the comb as compared to the Chambishi. And then rhenium, our fluid interaction indicator. So it's high in almost all the comb holes until you get to KN 211. Then there, it's higher in the Chambishi. Our iron, as well, iron speciation, you see that for some of the holes, especially KN 242, they're almost at par. But you also see that in terms of grade, it's not, the Chambishi is also nicely mineralized in KN 242. But then, by the time I get into KN 211, you're also seeing that the Chambishi is in a more reduced state compared to the comb. So now, we know that redox alone is not enough for mineralization, especially in the Chambishi, because what we've noticed is where the comb is barren and only the Chambishi is mineralized, it's not mineralized to a level that you'd expect for a fluid that we're saying has bypassed the comb and gone to just mineralize the Chambishi. So this is a structural model that Dave Selly has built. Thank you, Dave. And so here we're saying high-grade distribution at Chambishi level, it does correspond with inverted early basin structures. So you see where all those, so when you look at these, the reds are the higher grades, and the reds, and then the yellows and the greens are the higher grades. That's where KN 217 and KN 215 are, in that region. So we think for the Chambishi, yes, the fluid is migrating up, but it needs help. Because I think of all the carbonates, it can't fully or well travel to migrate to the Chambishi. So it needs structures that creates permeability. So, single fluid model summarized. So when we talk about single fluid model, we're talking of a vertical flow of fluid. And so we expect a vertical zonation. So we think of the fluids as coming from the Mindola. So then they go to the comb, and at that point, the copper content in the fluid is highest, right? So it interacts with the comb, and then precipitates copper and migrates up. So sometimes then you would see mineralization in the Nchanga, but it will still keep migrating until it gets to the Chambishi, where it drops copper. When you plot the sulfur ratio, the sulfur on this, you would see that actually sulfur is highest in the Chambishi compared to the comb, right? So by the time the fluids are getting to the Chambishi, you don't have a lot of copper in the system, so you end up forming chalcopyrite, sometimes a few times bonite. And the times that you actually see chalcocite and bonite, it coincides with areas where there are structures that have been mapped. So to conclude, So the comstarcoside bonite assemblage is a mineralogical signature of a copper saturated fluid interacting with a strong reductant. As we saw, vanadium and titanium show that the comb was deposited under more reducing conditions than the Chambishi. And then we see that we can use rhenium as a direct fluid interaction indicator. And then we also can use ion speciation to indicate or to show where the comb or the Chambishi is more reduced. And then the Chambishi preserves the signature of a copper depleted residue fluid. It has lower copper, lower rhenium in most cases, and the lower reduction intensity. But now I know that people are saying on the Zambian copper belt, some of these sulfides have been dated and they've shown different ages, right? So this is one of the hypotheses that we tested, but we do know that it could be that we actually have multiple mineralizing events that keep upgrading the copper. And so some of the work that's in progress is to date these sulfides. And so I think I have heard a lot of people talking about dating. It would be nice to interact and see if someone has done it before, how they've dated it, and how well that worked out for them, because we would like to actually do that. And one of the things that DevCeli is doing is just mapping scene rift architecture at the Mingomba and Kitwe Formation. Because before we do any drill hole, we usually make predictions about the grade in the Chambishi and the grade in the comb. The grade in the comb is easier to predict than the grade in the Chambishi, because some of these we know are affected by scene rift architecture. So it would be nice when our entire license or our entire ore body is mapped up and we can actually predict grade better, because then we know what the scene rift faults are that may be enhancing permeability. Yeah. So, thank you. But before I go, I would like to thank my line manager, Vubile. She likes to throw me in the deep end, but never without a rope, right? So I remember she came to talk to me and said, "Oh, can you give a talk at SEG?" Without hesitation, I said, "Yes." And then afterwards, I was like, "What have I done?" But that doesn't come without support. So I think I never say it enough. Thank you.